Hi. Until now we considered functions of one variable and their integrals. For example, we integrated speed over time to obtain distance traveled and a function of power consumption over time to obtain the total energy consumption. However, in engineering there are a lot of situations where you need to integrate functions of more than one variable. Let's look at an example. Suppose you are asked to design a suitable air conditioning system for an office building. Then you need to know the volume of that building. If the building has the shape of a rectangular box, like many office buildings, then estimating the volume is easy. It is the base area times the height. But what if it is not a box, like the Delft University Library? As you see, its roof has a rather fancy curved shape. How to determine the volume of a building with a curved roof? Here's an idea. For simplicity, assume that the building has rectangular base and vertical walls. You can chop up the building into rectangular columns, like cutting French fries from a potato. Of course, the volume of the whole building is just the sum of the volumes of the columns. Now, the volume of each column may still be hard to find, but we can approximate each column by a box. Then the total volume is approximately equal to the sum of the volumes of the boxes, and that is easy to calculate. We can make the approximation better by taking more columns. Let's make this idea more precise. We introduce coordinates x and y on the base of the building. Then the height of the roof is a function f of x and y. Now we divide the floor into small rectangles, say of area delta A each. Let's zoom in to one such rectangle. We can draw an imaginary column between this rectangle and the roof. Pick a sample point in the rectangle, say with coordinates x1, y1. Then the height of the column is roughly equal to f of x1, y1. The volume is roughly equal to this height times delta A, and geometrically this product represents the volume of a box with base delta A and height f of x1, y1. This we can repeat for each of the small rectangles. Pick a sample point, find the height of the roof over each sample point and draw a box with that height and the rectangle as base. Then the total volume is approximately equal to the sum of the volumes of the boxes. Does this expression look familiar? It is a two-dimensional analog of the Riemann sum. When we increase n, the number of rectangles, the Riemann sum gives a better approximation of the volume. The limit of the Riemann sum, as n goes to infinity and delta A goes to 0, is by definition the integral of the height function f over the base of the building. We denote this as follows: the double integral over d of f x, y dA, where d is the domain over which we integrate, in this case the base of the building. We use two integral signs to stress that there are two variables involved. In this case, this integral represents the exact volume of the building. Just as in the case of integration in one variable, it is very cumbersome to evaluate the double integral by using Riemann sums. Fortunately, there are ways to evaluate such integrals more easily. If you want to know how, have a look at the exercises.